Alright, welcome to the Chapter 3 homework review. Just like I've done before, I'll be going through some of the questions that we had the most difficulty with, and ones that I got a lot of questions about during the week as well. Now, predictably, on this homework, the most difficult problems for all of you were the lattice energy problems. These are pretty involved calculations, and one little thing goes wrong, and the whole number at the end comes out incorrect. So we want to understand how to do these for the upcoming test, and it is, as I mentioned in class, one of the most difficult topics to go through. Alright, so I'll give you one from this week's homework. This was the one we did the worst on, but there were several that we had trouble with in the same category of questions. The numbers here for the different parameters are variable, so I just sort of arbitrarily picked some numbers, and we'll see how we can go through and solve this. There's actually a small mistake on here. The delta H of formation should be negative. I'm sorry about that. So this should be minus 376, but all the rest of these numbers make sense. Okay, so we have an ionic compound M2X, and we want to calculate its lattice energy. Now, I've given you the equation a couple times. I didn't give it to you in class, but I've shown it on previous homework reviews, I think, or in the midterm review anyway. And for lattice energy, this equation works. So we have delta E for lattice. Now, in the homework questions, you had mixtures of delta H and delta E. They mean the same thing for our purposes, and on the exam, you'll only see delta E to eliminate confusion. But the lattice energy is going to be equal to that delta H or delta E of formation. It's given as delta H here. So the delta H of formation for the compound, and then you subtract 2 times the sublimation energy. Now, the reason we have to double this is because it's M2X. Alright, so there's 2 metals in there, so the terms that are associated with the metal, which is going to be sublimation and ionization, they have to be doubled. Alright, so then we have minus 2 times the ionization energy for the metal. Again, that's any term associated with the metal has to be doubled. So those are the terms associated with the metal atom, and then we have some for the non-metal as well. So we're given this energy here, which is the dissociation. So when we break down the compound into its element, the non-metal exists as X2. We have to dissociate it into atoms of X. So we're going to subtract 1/2 times the bond energy for X2, which is that number here. This is the bond energy. And the reason it's 1/2 again is because we only have one X in our formula, and this is X2, so there's only going to be half of an X2 involved in this cycle. I'll draw the cycle on the next slide if that's helpful for you. But for now, we'll just write out the formula, and then finally we have the electron affinity. We have to do 2 electron affinities for X because this is a -2 anion. And then that should be the last term we need. Alright, so it's these terms that we're going to add together to get the lattice energy. Now the reason, again, it's EA1 plus EA2 is that in M2X, now it's not immediately obvious from this, but we're not going to have any -4 anions. So our anions are going to be -1 or -2. We have 2 metals. We're only given a single ionization energy. All this pieces together to give us a compound that has 2 +1 metal cations and 1 -2 anion. Now, like I said, the given information sort of tells you the whole story, so you don't need to worry about us trying to trick you. The one piece of given information you don't need is the ionization energy of X, because we're not ionizing the nonmetal, we're adding an electron to it, which is electron affinity. But we need to have 2 electron affinities because it's a -2, so we're adding 2 electrons. And we usually, when you have 2 electrons being added, the sum of those first 2 electron affinities is a positive number, even though the first electron affinity is almost always negative. But adding a second electron is unfavorable. So those are some details we haven't seen before, but the general approach still works. And if we use this equation, we get the lattice energy is equal to minus 376 minus 2 times 125, which is the delta E of sublimation, minus 2 times the ionization energy, which is 523, and then we have minus 1/2 times the bond energy, which is 154, and then finally we subtract that electron affinity term, the combined EA1 and EA2, which is 325. And so if we work this out, we get Sorry, I didn't calculate this beforehand, so now I have to do it. Fairly large number, we get minus 2,074 kilojoules. Alright, now to convince ourselves that this equation is right, or if you prefer to draw out the cycle, which takes a little bit longer but is very helpful for understanding what's going on here, let's draw out the full cycle for this. So we have M2X, and we're interested in the energy of this process here, which is taking our two metal cations, 2M plus, as gas phase ions, plus X2 minus in the gas phase, combining them to form your solid ionic compound. And again, this unknown energy here is what we call the lattice energy. So we're going to solve for that. And we're going to go around a whole big cycle to get to there. So the first thing we have to do is break up this compound into its elements. So we have our M2X going to 2M's plus 1 half X2. Again, we need a half X2 because there's only one X in the formula. This is our negative delta H of formation, I guess this is given here. I'll be confused by delta E versus delta H. So this is our negative delta H of formation. We go back to our list of parameters. That parameter should have been minus 376. I mistyped that, but so we have plus 376 kilojoules to break up the compound into its elements, and then from here we have two steps involving the metal to get it into gas phase cations. So we're going to take the metal, 2M gas, we're going to convert the solid metal atoms into gas phase metal. And to do this, this is our delta E of sublimation, but because we have two metal atoms in our structure, we need to do this twice. We double that energy. So that's going to be 2 times, what was it, 125. Okay, so we have 250 kilojoules for that step, which is taking 2 moles of metal as a solid and converting it into 2 moles of metal as a gas. And then from here we're going to take and we're going to ionize the metal, so we have 2M plus, so we're going to lose an electron from each of those metal atoms. Okay, so to do this, it's going to be 2 times the ionization energy of the metal. There's 2 metal atoms, each losing 1 electron. So that's going to be 2 times 523. And then the last step is to dissociate, which we're going to have 2M plus gas plus 2 electrons, and we're going to dissociate our X2 here into X. So X2 is a gas, I didn't write that in, but it should be written as a gas, as we're given in the problem, and then we dissociate it into X. Now this is the bond dissociation energy for X2, but as we see in this, there's only a half of an X2, so we're going to take that number and multiply it by half. I believe that's 154, which is 77. Now here's where things are a little bit different for for this problem where we're making an X2 minus anion, so we're doing 2 electron affinities. So actually in this case, the electron affinity is not an exothermic step. So if we're actually trying to draw our cycle to scale, we would actually want to take this. This isn't really that important to draw it this way, but it does show us really what's going on here. So here we're adding both of these electrons to X to make an X2 minus, and that ends up being exothermic. So we're actually going to go up in energy a little bit more to get to here, which is the ions that are going to combine. And then finally that is going to be our lattice energy. So the cycle looks a little bit different here if we're drawing it to approximate scale, only because this last step here, which is EA1 plus EA2 for X, is endothermic. And that's usually the case when you're adding 2 electrons to a nonmetal. It's going to be an endothermic process for adding both electrons. So that goes up by another 325 before then you have your exothermic lattice energy step. So in this case, the only exothermic step, and I use the word exothermic meaning negative delta E, the only step that has a negative delta E is the lattice energy. All the rest of the steps in this cycle have positive delta E. a little bit different than when you have a 1 minus anion involved. So anyway, we have this cycle, and then we're going to just set everything equal to 0 and go all the way around. So 0 is equal to 376 plus 250 plus, what is it, 1046 plus 1046 plus 77 plus 325 plus the lattice energy. And when we solve for the lattice energy, we're going to get the same number we had above. So we just rearrange that and solve, and we get it. Make sure we get the same number, which we should. Yep, we get minus 2074. Alright, so you get the same number, of course, either way you do it. This cycle down here allows you to visualize things a little bit better and understand each individual step. But you know, again, these are our difficult problems, and the only way to master them is really to just practice them over and over again. So we still need some work to do in that. Alright, so the next question that I want to move on to, moving away from lattice energies, which are sort of in a special category of their own, we now have one that involves periodic trends. So which of the following has the smallest radius? Now, if we're going to use the periodic trends, remember that those really only directly apply to atoms, neutral atomic states. Here we have atoms and ions mixed together. So when you're doing a problem like this, the first thing you want to do is look at which row of the periodic table it is. That's largely going to determine the radius. So phosphorus is a third row element. It's in the n equals 3 part of the periodic table. Cl minus is also third row. It has a filled third shell now. We've completely filled that, made it S2P6, but it's still in the third shell. Let's go to the periodic table to convince ourselves of that. So phosphorus is here, chlorine is here, both in the third row. We have aluminum and sulfur, all in the third row as well. And then gallium, so these are all third row elements except for gallium. Now, when we're doing this, because gallium is in a totally different period of the periodic table, when you add an additional subshell, so the configuration of gallium, we now have a filled 4s and a partially filled 4p subshell. When you're going to a completely different subshell with a higher value of n, that's typically going to have a huge effect on the radius. So if we're looking for the smallest radius, we would expect gallium not to be the case because it's in the fourth row of the periodic table. So typically speaking, when you're looking for radius trends, the ones that are going to be closest to each other are those that are in the same row of the periodic table. If you drop down a whole row, you're going to have a very large jump in radius. But now we have to decide between all of these. And the thing to realize here is we're comparing neutral atoms and ions. And the basic trend is left to right. And most of you that did this picked choice B because Cl is the one that's furthest to the right in this row of elements. And many of you thought, well, if it's furthest to the right, that's going to make it the smallest. But remember, here we're comparing anions and neutral elements. And so the general rule is that, what we should realize is that anions are much larger than neutral atoms. We talked about why that is. When you add an electron to the outer subshell, you're going to increase electron-electron repulsions, and you're going to blow up that radius a little bit. But to understand how much it is, we do have a table of Ionic Radii in our book. If you have the book, it's where is that? It's figure 3.5 in the book on page 111. So if we compare chlorine and Cl minus, all right. So the atomic radii, we have to find that too. So here we go to another table in the book. All right, so figure 233, if you're trying to follow along at home with your textbook. The atomic radius of chlorine is 99. And from figure 3.5, we're talking about the ionic radius of Cl minus. That's going to be 181. Now you're not going to have this information in front of you when you're doing a problem like this, but what this illustrates is that when you go from a neutral atom to an anion, the radius increases a lot. We're talking about probably almost double or more than double in some cases. So when you're comparing neutral species to anions with no other information, you should assume the anions are larger. So So that means our anions, Cl- and S2- are likely to be much larger than other third row elements that are neutral, third row atoms. And so that leaves phosphorus and aluminum as the only choices. And we're trying to pick the smaller ones. Remember, when we go left to right, we decrease the radius. Phosphorus is to the right of aluminum, which makes it smaller. So the correct answer was A, but again, choice B was a very popular one amongst you because following just the periodic trends for atoms, chlorine is smaller than phosphorus, but when you add an extra electron to make Cl-, the radius is much larger. So definitely keep that in mind. Now another topic we had a little bit of trouble with on this homework was assigning formal charges. And admittedly, we learned this very recently and very quickly in class, and it's something you have to practice a lot. But Lewis structures are very important for what we do in Chapter 4 as well. So we need to be able to, to do these quite efficiently to be able to really attack the problems that are going to come at us in the next chapter. So one that we had, there were two questions on this structure and two related questions, and we have thionyl chloride, Cl2SO, and we want to know the formal charge on oxygen and number of lone pairs on oxygen respectively. Now the part that I think got a lot of us was that this little clause here then, assume all atoms obey the octet rule. So remember that when we say obey the octet rule, we're meaning for non-hydrogen atoms 8 and only 8 valence electrons. Okay, in many cases we see the central atom expanding the octet, which is okay for third row elements, like chlorine, sulfur, things below that on the periodic table. But when we say obey the octet rule, that means you cannot exceed 8 electrons on any atom in the structure. So here we wanted to draw the Lewis structure that had only 8 valence electrons on every atom and see what the formal charge and number of lone pairs was. So when we do that, we have to first count electrons to know how many there are. So for Cl2SO, we have chlorine, there's 2 of them, each has 7 valence electrons. So chlorine is S2P5, so it has 7 valence electrons, it's in group 7A. We have sulfur, which is right next to it in group 6A. We have 1 sulfur with 6 valence electrons. And then finally we have oxygen, which is also in group 6A, just above sulfur. So here we have a total of 26 valence electrons. If I did my math right, 14 plus 6 plus 6. So we have to draw a structure that has 26 valence electrons, but does not exceed the octet rule for any atom, or that it obeys the octet rule perfectly. So when we do that, we put S as the central atom as we're instructed. It's also the least electronegative. And we draw single bonds to everything. We're going to complete the octet of the outer atoms by putting lone pairs on. So each one gets 6 more electrons to now have a total of 8, including the 2 from the bond. Alright, so we have this structure here. We've used 24 electrons because we have 3 atoms, each with an octet. 3 times 8 is 24. So our last 2 go on the central atom. Now when we do this, when we check the octet of our central atom has 3 bonds and 2 lone pair electrons. So 3 times 2 from the bonds is 6, plus the 2 electrons is 8. So this structure here has the octet rule obeyed for all atoms. We don't want to start drawing double bonds. As it turns out, the best structure for this will have a double bond between sulfur and oxygen, but to obey the octet rule, we can't draw the double bond. The only way we can draw a double bond is to expand the octet of sulfur, which we're explicitly told not to do in this problem. Okay, so then now we have to evaluate formal charge and number of lone pairs. So for the formal charge on oxygen, remember each atom has a formal charge that's defined for it. So we start with number of valence electrons that oxygen has, which is 6. So that's valence electrons. We subtract from that the number of bonds that it forms. Oxygen just has a single bond in this structure. And then finally we subtract the number of lone pair electrons, the total number of non-bonding electrons, which is 1, 2, 3, 4, 5, 6. So these are all lone pair electrons added up. So 6 minus 1 minus 6 is minus 1. So in this structure, the oxygen has a minus 1 formal charge, and if we count, it has 3 lone pairs. Alright, so I didn't write all the answer choices here, but the one you should have selected has a minus 1 formal charge for oxygen and 3 lone pairs. Alright, so a very related structure is, or sorry, a very related problem is we want to determine the formal charge on chlorine in the structure for the perchlorate ion resonance form with 2 ClO bonds and 2 Cl double bond O. Alright, so this is a single bond, and this is a double bond. Alright, so we talked about with resonance, you have, a lot of times you have choices between how many double bonds you have, where they're located in the molecule, and so on. And we want to draw the resonance form as described here, which has 2 single bonds and 2 double bonds. So we need to know that the formula for perchlorate, which isn't given here, this is one of those polyatomic ions we should know, which is ClO4-. Alright, so we're going to start the same way we did before by counting up valence electrons, because we need to know whether the central atom has any lone pairs if we're going to calculate its formal charge. So the chlorine has 7 valence electrons, as we saw in the last one. And then oxygen, there's 4 of them, each of them has 6 valence electrons. And we have a minus charge, so we have to add 1 more electron. So 7 plus 24 plus 1 is 32 valence electrons. Okay, so when we draw this structure that we're instructed to do, we have chlorine, we have 4 oxygens, and in just about every Lewis structure we draw, or every one that I can think of anyway, you know, we're going to complete the octet of our outer atoms. But we're already told that we have 2 ClO single bonds, 2 ClO double bonds. We can draw those in right now without having, you know, take that shortcut. And we complete the octet on oxygen. So the oxygens that are single bonded get 6 more electrons to complete their octet, and the oxygens that are double bonded get 4 more to complete their octets. So when we do this, we've now used up all 32 of our electrons because we have 4 atoms with a complete octet. So our chlorine will not have any lone pairs in the structure. So we're done here, and we just calculate the formal charge. Alright, so the formal charge, as we saw before, is going to be equal to the number of valence electrons that that atom brings, or that atom has by itself. So that's going to be 7 electrons for chlorine. And then we subtract the number of bonds that it forms. 1, 2, 3, 4, 5, 6 bonds. 2 singles and 2 doubles is a total of 6 bonds. So it has 12 electrons, but they're shared equally, so we count them as 6 for the purpose of formal charge. And then we subtract the number of lone pairs on that central atom, which is 0. There are no lone pairs. 7 minus 6 is plus 1. Alright, so in this structure, in this resonance form, chlorine has a plus 1 formal charge. And so now you start thinking about, well, we could actually get rid of that formal charge by drawing 1 more double bond. So probably the best Lewis structure for this would have 3 double bonds and 1 single bond, as opposed to 2 of each. Alright, and then finally the last one, which involves drawing a lot of Lewis structures, is, you know, which of the following contains a carbon with a negative formal charge in its most important Lewis electron dot formula. Lewis electron dot formula being another way to say Lewis structure. Alright, so we have to draw Lewis structures for all of these and then calculate their formal charge. So for CO, this is actually a deceptively difficult one. It's only 2 atoms. We count the valence electrons. We have carbon has 4 electrons, oxygen has 6. We have a total of 10 valence electrons for this. And so when we draw this, we're going to follow the same approach we did before, which is to do carbon single bonded to oxygen. We complete the octet first of the more electronegative atom, which is oxygen. And then we draw so that's 8 electrons on oxygen, and that leaves us 2 more to put on carbon. So CO is a rare structure that has a lone pair on carbon. There aren't very many that have this, but this would be the first structure we draw. But if we look at this, you know, when we're drawing Lewis structures, the first thing we want to be able to do is complete the octet of all the atoms, if all possible. There's a few exceptions that don't complete their octet, but in general, everything wants to. And here, our carbon is woefully short of an octet. It only has 4 valence electrons, 2 from the bond, 2 from the lone pair. So to be able to complete the octet of carbon, we have no more electrons to add. We've used all 10 of our electrons, so we have no choice but to draw a triple bond. So if you take 2 of these lone pairs off of oxygen and make a CO triple bond, this is the only structure we can draw that was going to have complete octets in all the atoms, and that's the first thing you want to look at. Alright, we're back. Sorry, I had to stop there for a second. Alright, so we're back to CO here, and we have to calculate the formal charge on carbon. So we have 4 valence electrons on carbon as an atom, as we saw up here from the periodic table. We subtract the number of bonds. So carbon has 3 bonds, It's a triple bond to oxygen, so there's 3 total bonds, and then the number of lone pair electrons in carbon is 2, so 4 minus 3 minus 2 is minus 1. Alright, so this one does have a negative formal charge on carbon, so if we were confident in our ability to draw Lewis structures, we could stop here. Now to verify the rest of these, many of you picked choice C because it has a negative charge. We'll verify as well that does not have a formal charge on carbon. Let's look at the rest of these. So CO2, we've seen this one now in class, I believe, and also in the exam review we did. So if we draw CO2, here we have 4 electrons from carbon plus 2 times 6 from oxygen. So we have 16 valence electrons on CO2. When we draw the Lewis structure, we would start again by completing the octet to the oxygen, which is more electronegative. When we do that, we've run out of electrons, but we only have 4 electrons on carbon, so again we have to draw 2 more bonds. And the best way to do this while minimizing formal charges is to draw 1 double bond to each oxygen. So a pattern we're starting to see is that oxygen likes to have 2 bonds. CO is a weird one where it has more than 2, but CO2 we have 0 formal charges, and we can verify that for carbon because we have 4 valence electrons minus the number of bonds, which is 4, minus the number of lone pairs, which is 0. So CO2 has no formal charge on carbon. CO3 2 minus, which is carbonate. Okay, we have number of electrons is 4 plus 3 times 6 plus 2 more for the negative 2 charge. That's going to be 18 plus 2, 24 electrons. Okay, so we have 24 valence electrons for carbonate. And when we draw the structure for carbonate, we start with single bonds to oxygen. And that's all 24 of our electrons, 3 oxygens, each with an octet. But at this point, we have an incomplete octet on carbon because we only have 3 bonds for a total of 6 electrons. So we need to draw 1 double bond in this structure to complete the octet on carbon. So we take off a lone pair from this oxygen, for example, and draw it there. Now we should recognize that this has 3 resonance forms possible, where this double bond can be either here, it could be between this carbon and oxygen, this one, and so on. But if we draw that double bond in any of those resonance forms, we calculate the formal charge on carbon. 4 electrons on carbon, 4 bonds, 0 lone pairs. And this will also have a 0 formal charge. So the formal charges in this structure are on the oxygens that have single bonds, but not on carbon. CH3OH, we're running out of room here, but CH3OH, we drew this one, I think in class or in the review. I'm getting foggy and everything, but CH3OH has this structure. And we see in most of these compounds that involve carbon, carbon tends to have 4 bonds, and when it has 4 bonds and no lone pairs, it has 0 formal charge. So that's the same here, and then HCO2H, which we'll draw, also has this structure. This is not the easiest one to draw with our current knowledge, but if you draw 4 bonds to carbon, if you complete all the octets of everything, this is the structure you get, and you have 4 bonds to carbon, which also gives you 0 formal charge. Alright, but CO is the only one that has a negative formal charge, and really it's a very rare structure that has a negative charge or a formal charge of any kind on carbon. Most structures, B through E in this case, or any other ones you can imagine for the most part, they're going to have 4 bonds to carbon, which gives you 0 formal charge. Alright, the last one I want to go through then that is not related to Lewis structures is relative bond energies. So we're given pairs of bonds here, and we need to pick which one is stronger. So the 2 things we want to look at are bond order, which is whether it's a single, double, or triple bond. And then the second thing we can compare if they have the same bond order is bond length. So bond order is probably the more important one, because if you go from a single to a double bond, the bond energy increases dramatically. Alright, so this is the more important of the 2 to think about. But in many of these examples, the bond order is the same, so then we have to look at bond length. So for bond order, higher bond order equals greater bond energy or stronger bond, however you want to think about it. And then for bond length, it's sort of an inverse relationship. The shorter bond length gives us the greater bond energy. Alright, so those are the 2 things we're going to look at for these. So if we have CF or CCl, remember that we have the bond distance. So the bond order is the same. These are both single bonds, and the bond length depends on the atomic radii that are involved. So both of these have carbon, and if we think about periodic trends, chlorine is bigger than carbon, so this is going to be the longer bond of the two, and CF is going to be shorter. Okay, so because chlorine is larger than fluorine, there's going to be a longer distance between those nuclei in CCl. So if we're trying to pick the greater bond energy, we wanted the shorter of the two, so CF is going to have a greater bond energy because it's a shorter bond. In number 2 here, we have carbon-carbon bond in C2H4 or the bond in F2. Alright, so we have to be able to draw C2H4 to be able to do this. So for C2H4, we have hydrogen only gets single bonds, and then we have to draw a double bond between the two carbons to complete the octet and use up all of our electrons. So C2H4 looks like this. Again, 4 bonds to carbon is a very typical arrangement. And so this is a double bond. And then F2, if we draw the Lewis structure for that, is a single bond. Okay, so F2 has 14 valence electrons, which means we have a single bond between them. Alright, so of these two, we would expect the double bond to be stronger. As it turns out, the bond in F2 is anomalously weak, so this is one of the weakest single bonds out there, F2. But even without knowing that, because this is a double bond, the bond in C2H4 should be stronger. And then finally, CO versus C double bond. Now, if you're comparing two like this becomes very simple because the only difference between these is bond order. This is a double bond. Higher bond order means larger bond strength. So for each of these pairs, we would pick the one with the stronger bond strength or the greater bond energy, as is worded here. So that's going to be CF, this double bond here in C2H4, and then C double bond O. Alright, that takes us to the end. As always, you can ask for any clarification on these, and I wish you the best of luck on your exam this week.